I'm here at this meeting that's about impact and invention. So you're probably thinking I must be an applied mathematician if I come from mathematics. But I come from pure mathematics originally. So what am I doing here? Well, gradually over the last few years, I've started to get to be in a position where I've sort of got 1 foot on each side of this classic division between the applied mathematicians who try to do useful things and the pure mathematicians who love the austere beauty of their subject and are completely uninterested in doing useful things. So I want to reflect a little bit on the nature of this division as a little bit of a metaphor for some of the themes that have been coming up across the discussion today. So I'm going to go all the way back to the beginning, and I mean way, way back. Human development, Homo sapiens, right? Innovation is in our DNA, quite in a literal sense. Because every time we encountered a problem in the early days of Homo sapiens, we innovated our way around it. Not enough food? Let's turn that grass into something we can eat. Let's turn those grazing animals migrating across the fields into something that we can put in a pen and farm. Right? We continually innovated past each of our problems. But here's the interesting thing. If you go back 40,000, 50,000, 60,000 years, there was Homo sapiens and there was also the Neanderthals, living in parallel in different parts of Europe or the world at the same time. And the curious thing is the recent archaeological evidence seems to be that the Neanderthals were more creative than us. They innovated more than us. They did things more differently. In the sense that you look at Homo sapiens and they figure out how to make an axe blade. And they make that same axe blade using the same stone chipping technique for 10,000 years across multiple continents. Whereas the Neanderthals would do it differently. They'd make one axe blade and make a different one, make a different one. There was much less uniformity in the technologies that they developed. But they died out. Whereas Homo sapiens, with our intellectual conservatism, that also seems to be written into our DNA, we persisted. So the abstraction of this, being a mathematician, I like abstractions, is the proverbial box. We're always trying to think outside the box when we talk about innovating. So I can't help drawing a picture here. Here's the box. Now the problem is if you want to really innovate, do something that changes the world, you're probably trying to think outside the box. Because all the good ideas that were in that box, they've already been exploited. The mileage we can get from that box is saturated now. So how do we get outside the box? Well, the problem is if you're trying to think outside the box, you're stuck. That means you're already in the box. You're trapped. The box is the prison. The solution is to not try to get outside the box, is to do something different, to get in a different box. So here's some other box. And maybe this one was the applied problems that were important, and this one is, for example, in my case, pure mathematics problems that don't seem so important. But you might start here, and being in the second box, you're free to move around within the box. Very hard to get out of it, but you can move around within it. And maybe you moved over to there, and by doing so, you haven't realized it because you weren't paying attention to the first box, but you've now freed yourself from the confines of that first box. So this is a metaphor for one way in which innovation processes can happen. And I want to give you a couple of examples of where this is really meaningful and why it's so useful to allow ourselves the freedom to work in these other boxes that aren't necessarily the one that we think is the really most pressing, world-changing problem. So being a mathematician, I'll give you 2 quick stories from mathematics. The first one is a famous French mathematical prodigy, Galois, back in 1830, shortly before his 21st birthday and shortly before he perished tragically in a duel. He came up with some very abstract ideas in algebra, ideas about arithmetical systems that have only finitely many numbers. Modular arithmetic is called if you've ever worked with remainders. This is the beginnings of number theory. So this was 1830. Pure mathematicians got very interested in this. Applied mathematicians were not interested. That's not useful for doing the calculations for things that we're interested in. Then we fast forward to 1960, 130 years later, and Reed and Solomon came up with an idea thinking about linear algebra, so vectors and matrices in this modular arithmetic system. And they came up with a way of encoding and transmitting information where errors could be detected and corrected. Very lovely idea, but it was very difficult at the time to put it into any kind of concrete practice. We didn't have the electronic technology to do that. It took a little while, but then I think the next date I have is 1977. So 17 years later, almost 2 decades, NASA had finally developed some systems that could implement this, and they used it on the Voyager space probe to send signals back to Earth. So you might have heard Voyager's been in the news recently because it's been getting senile and sending nonsense signals, but it's still using that same code. So then 5 years after Voyager was sent up using this code, the innovation happened. People realized, oh, we can use this to make CD-ROMs. And this is the encoding that CD-ROMs use, and it leads to the amazing effect that if you have a CD-ROM disk and you drill a hole in it, you can still read all the information on it perfectly. You think that by drilling a hole, you've destroyed it, but no. All the information is entirely intact. You can actually do this experiment, but don't do it with a CD that you value. Of course, nobody uses CDs anymore. We use other digital transmission methods and digital storage methods, but a lot of them use the same code or variations on the code. Yeah. Yeah, right. So that's one example where something that was initially completely useless, esoteric, and abstract turned out to be world-changing. My other example is Riemannian geometry. So the geometry of curved shapes, possibly high dimensions. So Riemann came up with the idea, proposed this branch of mathematics in 1857. But of course, there was no possible use for that. That was just pure mathematics. Mathematicians got very interested in this, and then sometime later, 60 years or so, Einstein comes along and realizes that this is just the mathematics he needs to develop his theory of general relativity. Of course, general relativity was interesting theoretical physics, but that's not useful for anything. I mean, the best it could be useful for is predicting the precession of some aspect of the orbit of Mercury. So some technical detail of the orbit of Mercury. Turns out general relativity worked well for that, but nothing here on Earth could possibly be general relativity. Now you fast forward some decades. Turns out, if you, I left my phone up there, I was going to pull out my phone. You have, all of your phones use general relativity to make the corrections that are needed to make GPS work. Right? Speed of light is 300,000 kilometers per second. It's pretty fast. And general relativity means that the clocks on satellites in orbit run a little bit differently from the way you would expect if they were on the surface of the Earth. And this difference, this discrepancy, is around 45 microseconds per day, which is not much. But relative to that huge speed of light, that's enough to mean that your estimate for where your position would be is off by about 10 kilometers per day, and that keeps adding up. So GPS just wouldn't work without general relativity. Another example, I feel a little bit funny about this because making money for money's sake is looked down upon a little bit, but there's a hedge fund called Renaissance Technologies, founded by a guy named Jim Simons, who was originally a pure mathematician, worked in differential geometry. He left pure mathematics, founded this hedge fund, where he used ideas from big data combined with differential geometry to optimize a trading strategy. And they've become, I think, effectively the most successful hedge fund in the entire world in the history of all hedge funds. And they've become a huge benefactor for mathematical sciences research. But this was based entirely on mathematics of differential geometry, which nobody would have predicted would be useful for the stock market in the 19th century when Riemann was doing this. So those are my two stories, and that's about all I want to say. And I just want to close by saying, we don't know where the next idea that changes the world is going to come from. And if you go looking for it, you're probably looking in the wrong place. So you should instead go looking for something that's interesting, that's exciting, and be open to the possibility that you might stumble in the process on something that allows you to change the world, or allows somebody you know, or somebody who knows somebody who knows somebody who knows you, to change the world with that idea. And I'll finish there. Thanks very much.